Hi, I'm Matthew Gilbert from the University of Sheffield in the UK. I'm going to give you a flavour of the work we've been doing in collaboration with colleagues from Arup and Limit State on holistic layout optimization of building structures. Bit of background. Climate crisis demands we take action. We know traditional building designs are often not that structurally efficient. What can we do about it? Well, we can change the shape or the size of members, but also changing the layout can reach very large savings, and we urgently need tools capable of identifying more efficient structural layouts for building structures. What methods are we using? Well, we're using ground structure based layout optimization or topology optimization methods. So in this particular case, we have a gravity loaded cantilevered building example, slightly artificial, but what we have is a roof area with loads applied, and we can identify the most efficient layout of grillage members or beam members to withstand that loading. For the vertically aligned regions, we can use truss layout optimization methods to identify the most efficient arrangement of members. In both cases, the layout optimization methods that we use are very, very efficient, so we can solve large problems in a few seconds. And we've implemented these techniques in the Peregrine plugin for the Rhino Grasshopper parametric software. And so what you can do as a user is basically identify regions, whether they be truss regions or grillage regions. You then feed those in to the solver, solve the problem. So you solve the layout optimization problem in stage one, and then to improve the practicality of the solution, rationalize it, you can use stage 2 tools to do that. So what I'm going to do is just demonstrate this through a very simple entrance canopy, designed to come in all different shapes and sizes, from the very simple cantilevered example shown in the left to examples where we're also making use of structure below or above the flat roof, as you can see. So what we've assumed here is we've got an 8 by 6 meter flat roof with a couple of column supports, and also one of the long edges we're assuming has a simple support. And what we've got here is a reference design which comprises a series of orthogonally oriented beams, either hogging or sagging, to carry the load. And we're taking that as the reference for 100% volume design. Now, if we allow those beams cross sections to actually taper along their length, then we can realize very large savings. Actually, the tapered beam example is little more than half the volume of the original one. And we can mix things up even more by allowing the grillage optimization tool to do its work and identify a more efficient beam grillage arrangement to carry the loading. And we end up, as you can see, with a significant further reduction in volume. Next, we can also allow structure, for example, above the flat roof section, and we can get fairly sizable savings in volume with uniform beams, with tapered beams, and also with the optimized grillage. So the final case, we have a volume which is now less than 25% of the reference volume. So you can see you can get very large savings by using this holistic optimization tool, albeit this is a fairly idealized, simple example. Here we've got a couple of renders. So the one on the left shows a render of the last structure we looked at. on the previous slide. And then on the right, we've actually had some stage 2 rationalization, so some automated tools to rationalize the solution and get a somewhat more practical solution. Still rather complex, but I think potentially buildable. Next example, simple multi-story building, and a similar outcome. We can get very, very large reductions in volume if we simultaneously optimize the framing and the locations of beams forming the floor plates in this multi-story building. In this case, the right-hand side structure is around a third of the volume as the one on the left, the more conventional one. So wrap up, numerical optimization is a powerful tool for use at the conceptual design stage. We can combine truss and grillage optimization to allow efficient design concepts to be identified. And if you're interested in trying this functionality, it's available in the Peregrine, or will be available in the Peregrine plugin later in 2021. The structure on the top right shows an early application of optimization in practice by our colleagues at Arup. The structure on the right is some of the examples that we're currently looking at with the new Peregrine functionality. So potentially we can solve much more complex problems than the ones that we've looked at in this presentation today. And then finally, just like you draw your attention to a web app we developed to increase awareness of the power of truss optimization, and also some recent papers published in case you have interest in this area. So thanks very much, and I'll look forward to taking questions during the Q&A session.